So Einstein, special theory of relativity, the first one that he worked on, the one that he came up with some answers to his questions, they're based on a couple of postulates. One is that, he introduced what's called an inertial frame of reference. So what is, that's a word that we use a lot. What is an inertial frame of reference? So an inertial frame of reference is any frame of reference where Newton's first law of motion applies. The first law of Newton's second law is F equals ma. That's the second law. But the first law is the net force is equal to 0. So that, acceleration is 0, right? So, and that means that if an object is at rest, it stays at rest. But if the object is moving, it will keep on moving in a straight line at a constant speed. And both of those, that's what inertia is, translational inertia, right? A measure of the translational inertia of an object is it's the amount of mass that it has. Galileo was the first one to introduce this concept of inertia. The more mass an object has, the more its tendency to maintain its motion. If it is at rest, it wants to stay at rest, but if it's moving, it wants to keep on moving in a straight line, right? The more mass it has. So if the object is at rest, it wants to stay at rest. That's because of inertia. But if it's moving, it wants to keep on moving in a straight line at a constant speed because of the inertia. So an inertial frame of reference is one where the Newton's first law applies. So if an object is at rest, it'll stay at rest. If it's moving, it'll keep on moving. So what can we think of an inertial frame of reference? So we can say, for example, this room is an inertial frame of reference, right? The marker is at rest and it stays at rest. I'm not doing anything to it, right? Just leave it alone. It is at rest, it stays at rest. Its acceleration is 0 because the net force acting on the marker is 0. But if the marker is moving in a straight line, moving in a straight line and some of the forces is 0, then it'll keep on moving in a straight line at a constant speed. So that could be, for example, a train that's passing by next to this building. Well, there are no trains nearby, but imagine a train going by at constant speed in a straight line. So, that's an inertial frame of reference. A car that somebody drives in a straight line at a constant speed, constant velocity, 0 accelerations, that's an inertial frame of reference. So Einstein said that the laws of physics in any inertial frame of reference are the same. They're all equally valid. So the laws of physics in this room are equally valid in a train that moves at constant velocity, equally valid in an airplane that moves at constant velocity, just constant velocities, no accelerations. And the other postulate of the theory of special relativity is that the speed of light in vacuum has the same value, 3 times 10 to the 8th meters per second, although I think it's more like 2.9999, let's just say 3 times 10 to the 8th meters per second, regardless of who's making the measurement of the speed of light, and regardless of how fast the source of the light is moving. So if I'm, for example, in so let me just tell you what that means. Let's say this is the ground, right? So ground. And this is me. At rest. And I take out a laser pointer. And I shoot a beam of light. Yes? So, laser pointer, shoot a beam of light. Okay? So, how fast does a beam of light travel relative to me? It travels at 3 times 10 to the 8th meters per second. What if, as I do this, somebody is in a spaceship traveling very fast, let's say half the speed of light, this way. So suppose that there's someone in a rocket over here, this thing is traveling at 1/2 of the speed of light in vacuum, so that would be what? 1.5 times 10 to the 8 meters per second. And someone in here measures the speed of this light that I, emitted using this laser pointer. So what is the speed of this light that this person measures?
10 to the 8.
They measure exactly the same thing. 3 times 10 to the 8. Or, let me change it a little bit. What if I don't have the laser pointer? Somebody's driving that, and then somebody stands over here, and this person takes out the laser, and this person shoots a beam of light. So to this person, the speed of this light is c, or 3 times 10 to the 8. Now, what will this person say at rest on the ground, watching this rocket go by at half the speed of light? What will this person say is the speed of this light?
3 times 10 to the 8.
What's that? 3 times 10 to the 8. But this is counterintuitive. Because let me pose this question in a different framework. So, according to Einstein's theory, you're right. This person, if it's me, I would say that the speed is c, which is 3 times 10 to the 8 meters per second. So, according to Einstein, anyone who makes a measurement of the speed of light in vacuum, anyone, I don't care if the person is at rest or the person is moving. I mean, this person is moving, and to this person, light travels that fast away from him or her. And this person who's at rest over here, not moving with the source of the light, right, will also measure the same speed of light. And this is counterintuitive because in Physics 185, you learn about relative velocity. And when you learn about relative velocity, you consider the following problem. What if this is the ground, and this is someone at rest, and there's a truck? Those are big wheels, but it's a truck. So, truck. And someone is driving this truck, and suppose the truck is traveling relative to the ground at 60 miles per hour. And someone gets, it's on the truck over here, and this someone takes out a baseball. And what if this person pitches the baseball forward at 40 miles per hour? So, this person throws the base, it's on the truck is moving on the ground, right? So this person takes out the baseball, throws it forward in the direction that the truck is traveling at 40 miles an hour relative to him or her. What is the velocity of that baseball when it leaves the thrower's hand as measured by this person?
100 miles an hour.
How much?
40 miles an hour.
100.
No. We get 100 miles an hour. But that's not what happens over here. So either this is wrong or that's wrong, right? So what you learn in Physics 185 is that in classical mechanics, you could say, let's say, the person is at rest on the ground. So use G for the ground, use T for the truck, and use B for the baseball. And the question was, what is the velocity of the baseball relative to the ground, which is the same relative to this person, because this person is at rest relative to the ground. So you want to know, what is the velocity of the baseball relative to the ground, right? So the rule is this, right? With relative velocity problems, those of you who took 185 from me, you kind of remember this, but I'll write something crazy here. So if I want to know the velocity of B relative to M, so you can use an expression like this. Okay, I'll stop. I'll stop here. Oops. could have gone on, but I just, I think I'll still get the point across if I do this right. So for relative velocity problems, if I want to know what this is, so the trick is that the first letter here is the first one here, the first subscript. And the second one of the quantity that we want to find out, right, is the last one. Can you see them? So this is that. And this one is the last one. But then what about all the other letters? Well, the second one here is the same as the first one in the next term. The second one here is the same as the first term in the next, as the first letter in the next term. The second one here is the same as that one. This one is the same as that one. So I could have continued. I could have written WZ and then VZE and then VED and then D and then finish. We could have done that. So in this problem, what we want to know is the velocity of the baseball relative to the ground, right? So go right at baseball. So using these rules over here, right? Using this rule over here, the first letter here is B, but then the last one has to be G. And whatever I write here, I have to write over there. And what is the letter that I'm missing? T for truck, right? So therefore, I should write over here T and T. So what is the velocity of the baseball relative to the truck? Baseball relative to the truck is 40 miles an hour to the right, plus. And what is the velocity of the truck relative to the ground? Well, the truck relative to the ground is traveling at 60 miles an hour to the right. And you learn in the first chapter of Physics 185 how to add vectors. Two vectors are pointing in the same direction, right? 40 and 60 gives you 100 miles per hour to the right. And if we were to do this experiment, that's what you're going to get. So this equation over here was first thought by Galileo, and Galileo died. When did this guy die? I think he died in the first 3 months of 1642. March, February, I don't remember. February, March of 1642. That's when he died. And Newton was born the Christmas after that, 10 months later, Newton was born. So Newton never met Galileo. So Newton, there was a time interval of about 10 months or so when Galileo was dead and Newton had not been born. But Newton, advanced this theory, so this is known as the, as a formula by Newton and Galileo, although I want to credit Galileo because he came before Newton. It's not like they did it together. So according to Einstein, though, if I said, L for light, R for the rocket instead of the truck, and G for the ground, like this person here, if we use this expression over here, right, then we would get that what we want to know is the velocity of the light relative to this person, right? So the velocity of the light relative to the ground, if we use, then we would be L is the first letter, and then there's something else, plus whatever this is, that's going to be that one, and then the last one has to be G. And what is the letter that I'm missing?
Rocket.
The rocket, right? So then R. So the light relative to the rocket is C to the right, plus, and the rocket relative to the ground is half of C to the right. So this should be 1.5 C to the right, which is more than the speed of light, as measured by this person. But this is wrong, experimentally. So what Einstein did is he said, the fact is that this person is going to measure C, and this person is going to measure C for the speed of light. So this equation is wrong. It has to be that this is wrong. I have to fix this so that in these types of problems where these velocities are very small compared to the speed of light, this works. But if I use that same formula and I consider it in this other problem where things are moving, at the speed of light, half the speed of light, then I need a new formula. A new formula that in the limit of speeds very small compared to the speed of light in vacuum is going to give me that. Because that's good for those speeds. But it's not good for this speed. So he says, I have to fix that. Right? And I'll tell you the answer, and I'll show you later on how that comes about. But what he did was, he said VLG equals VLR plus VRG, and then 1 plus, and then you multiply those two. And you divide by the speed of light squared. So this is how he fixed it. And this expression, this is what Einstein wrote, and this expression is good for this problem, and it is also good for this problem, because if I took those speeds and I put them into this formula, what am I going to get in the denominator? Just in the denominator. I'm going to get 1 plus. Okay, the speed of the, for that problem, the speed of the truck, let's say, relative to the ground is 60 miles an hour. Okay, so, and then the speed of the baseball is like 40. Then I have to divide by the speed of light squared, which is, this is like 3 times 10 to the 8, and then I've got to square that, which is like 9 times 10 to the 16. Essentially, this goes, then you can neglect that. And then you just get a 1 downstairs, and then you recover what you had over there. But if the speeds, both of them, are comparable to the speed of light, then you cannot neglect that term. So what Einstein then did was that for this particular problem, you have the velocity of the light relative to the rocket. So that's c to the right, plus the velocity of the rocket relative to the ground. That's half of c to the right. And then this is 1 plus, and then what's the magnitude of this? What's the velocity of the light relative to the rocket? C. And what is the velocity of the rocket relative to the ground? Half of c, but then I have to divide by c squared, right? So what happens is this. How much is c times c? C squared. Divided by c squared? 1. So what do I get in the denominator? 1 plus a half, so I get 1.5. And what is c to the right plus a half of c to the right? 1.5 c to the right, so the 1.5 is canceled, and I get c to the right. So this is the correct, or I should say, this equation that Einstein came up with for this relative velocity problem that we discussed in Phys 185, right? Just know that this equation, this formula that you learned in Phys 185, this is really an approximation to the truth. The truth is that one. This is just an approximation. It is a good approximation the more slowly the objects move relative to the speed of light, compared to the speed of light. But that one works always. This one works sometimes, when the things are moving at speeds that are small compared to the speed of light, which for Phys 185, you consider a truck, a baseball, even an asteroid, whatever, the space shuttle. Even though those things are moving fast to us, they're still nowhere close to the speed of light in vacuum. The space shuttle orbits around the Earth, say, one of these communication satellites at like 17,500 miles an hour, which is fast, right? Imagine that would be a very big speed limit ticket, right? Ticket for exceeding the speed limit. And that can make a trip around the Earth in an hour and a half, 90 minutes or so. But it's still not compared to the speed of light. Light can go around planet Earth 7.5 times in 1 second. Forget about 90 minutes. 1 second, 7.5 times. So it just doesn't compare. So for the problems that you solve in classical mechanics and so on, objects, macroscopic objects, big things, then this is good. It's good enough. It works. Okay, it gives you good answers, right? It's a very good approximation to the truth. But the truth is this, which then cannot be overlooked. If both of these speeds over here are comparable to the speed of light, you must use this expression. So this is one of the corrections that Newton made to the theory by Newton, that Einstein made to the theory by Newton. He says, okay, sorry Newton, I have to fix this over here, because this is only good in this realm of small speeds compared to the speed of light. What if we have objects that are moving very, very, very fast? Then we have to fix that, make it more general, right? Not just good in this limit the small speeds, but what about all possible speeds, right? So this is the one. So I'll show you where that comes from later on. So this is a formula that you learned in Phys 185 that you have to unlearn, because that's the new one. That's the one. So one of the postulates, and this was a result of an experiment done by Michelson and Morley in the late 1800s, and so people were trying to explain that, and it wasn't agreeing with that other formula. So Albert Einstein worked on that problem, and this was his solution, and it was a good solution. Oh, that's one thing, and another thing over here, right? Quiz on chapter, what is it, 35? This Thursday?
I think
Or
it's chapter,
34?
I think it's chapter 34.
34, right?
So I think the last one was 33.
Okay. You want a quiz in chapter 34? 35? 36? On Tuesday? It'll force you to study that so that then you're ready for the test on Thursday? It'll put it in perspective.
35 or 36?
How about both of them?
Oh.
Because if I say 35, you're not gonna study 36 until then you'll be studying it the day before the test. So how about I'll choose a problem between one of these chapters.